Good morning, everyone, and welcome to our panel discussion on the future of telecommunications. If you have questions for the speakers in the session, please enter them into the chat feature. And now we are pleased to welcome our moderator, Diana Cooper from Hyundai Urban Air Mobility. Diana, the floor is yours.
Thank you. Good morning, everyone. Welcome to the Future of Telecommunications panel. I'm Diana Cooper, Head of U.S. Policy for Hyundai Air Mobility. I'll be your moderator for the session. We have an incredible lineup of speakers from government and industry representing a wide range of technologies, from terrestrial infrastructure to space-based solutions and some solutions in between. We're going to be exploring the different technologies, how they complement and compete with one another, and we'll also be diving into some of the investments and strategic partnerships that our panelists have made over the last year. I'm going to kick things off by introducing each of our panelists briefly. They'll each have about 5 minutes to provide their background, introduce their organization, and share what they're most looking forward to getting out of the panel. After the brief intros, we'll go into questions for the panelists, and please submit your questions online. We'll be happy to take them near the back half of the panel. So with that, let's dive in. Our first panelist will be Philip Mcallister, Director of Spaceflight at NASA. Over to you, Phil.
Thanks, Diana. I appreciate you guys inviting me to this panel. I'm actually filling in for Badri Younes, who at NASA headquarters has responsibility for our space communications and navigation area. But I had a very long background in telecom before I joined NASA about 15 years ago. And I've really since then been focused more on the human spaceflight area, but now I'm advising Badri and his team on commercial telecommunications capabilities. What I found is that at NASA, we have a very strong technical capability in telecommunications, but not always the best understanding as to how the private sector operates, what their incentives are, what sort of motivates them. So my experience in the private sector before coming to NASA has really facilitated that. And being able to sort of execute these public-private partnerships, which NASA has been really using extensively, primarily in the last 5 years, I've been able to sort of help fashion those partnerships in sort of the traditional win-win for government and industry, because it is important that you align your goals between industry and the government when you enter into these partnerships. And it's really, you got to be very, very clear going into those partnerships what you're trying to get at. So I will say that the good thing is that within the telecommunications sphere at NASA, I haven't received a lot of resistance to moving to more commercial services. I experienced a lot of that in the human spaceflight world, but I think over in the telecommunications sphere, there's definitely a recognition at NASA, particularly that low Earth orbit telecommunications, we can rely on the private sector for those capabilities without having to build a lot of infrastructure ourselves. So that's my main message. I'm looking forward to having this conversation with everybody today, and I'll kick it back to you, Diana.
Thank you, Phil, and we're really looking forward to your insights, in particular on the public-private partnership side of things. Our next speaker on the panel is Ed Knapp, the Chief Technology Officer at American Tower Corporation. Over to you, Ed.
Hi, everyone. Good morning. Thanks, Diana. I also want to thank Rob Meyerson for giving me the opportunity to speak today as part of the AIAA conference. I would say fundamentally this is an exciting time relative to telecom in general, and American Tower is at the heart of that. We have essentially a digital infrastructure business. We're looking at multi-tenancy to try to improve the economics of deployment of different infrastructure. Our fundamental business is macro towers. Throughout the world, we have close to 180,000 plus macro towers serving 20 countries. And we've been working very aggressively in new future technology areas. So when I joined American Tower, I spent 30 plus years in the wireless industry, working from 1G to 5G, most recently before American Tower with Qualcomm on 5G, and a lot of the research that went into the current standards that are hitting the market today. Some of the new areas that we're looking at American Tower include wireless connectivity, particularly as we look at apps and LEOs and how those can play a role in providing coverage and capacity for the networks terrestrially. The work around 5G is fundamental and all the rollout of that technology. Fiber optic communications and how that provides different transport and interconnection options terrestrially for bandwidth. looking at edge data and edge computing, which improves things related to whether it's drone or automotive and other applications. And ultimately, we're working on power and energy solutions for markets where the infrastructure for the grid is poor or weak. And so there's a lot of work in renewables and storage. So those are the types of things as a company we're doing. And fundamentally, there's been transformation that's occurring now in certain markets when we get into 5G. So a lot of work's going into how is 5G going to impact the telecom networks? How does that play a role into the work that's going on in space? There's non-terrestrial networking standards that are being positioned now within the 3GPP, which is the industry forum that delivers on that. So I'm looking forward to the discussion today on a lot of those topics and working with the folks on this panel to discuss this. Thank you.
Thank you, Ed, and we're really looking forward to your insights. Unfortunately, we don't have a mobile network operator on the panel. We don't want to send the wrong signal out that there is no future of telecom without mobile network operators. So it'll be great to get Ed, given your background, to kind of weigh in on 5G and that aspect as well. Our next speaker on the panel is Jonathan Hoffler, the Vice President of Starlink and Commercial Sales at Spacex.
Thanks, Diana, and thanks to my panelists and for the participants dialing in this morning. A lot of excitement happening at SpaceX over the last few weeks. We recently brought back Bob and Doug, our NASA astronauts, back from the International Space Station. We did a hop test of our Starship next generation vehicle, which is really exciting if you haven't seen that. We got selected as the US government, one of their launch vehicle providers of choice. And if that's not enough, we're launching Starlink satellites. So no shortages of excitement and work to do at SpaceX. On this panel today, talking about Starlink connectivity, we are rolling out service to our friends and family in the Pacific Northwest. Yesterday, we had our 10th launch of Starlink satellites, 11th, depending how you count it, but we have over 655 satellites launched to date. Which is enough to provide connectivity in the northern latitudes. And we're planning on launching roughly every 2 to 3 weeks to fill in the rest of the globe. And we're on pace to do that. So for those of you who don't know about Starlink, the total global constellation targeting is 1,440 satellites, of which a good number of those are already on orbit. But we're also vertically integrated, similar to the successful architecture for Falcon 9, where we built the engines, the tanks, the fairings, the Dragon capsules. We're taking the same approach to Starlink, and not only have obviously great access to space, but we're building our own satellites from the ground up, our own ground side infrastructure and gateways, and also our consumer user terminals. So a lot of great things going on. Happy to take your questions. Excited for what this technology is going to bring to the globe. Over the last several months, we've been getting more and more public about our technology. We've been focused for the last couple of years on getting the technology right, but there's been an outpouring of demand and excitement, not only for consumers, but across all the enterprise verticals for connectivity. So a lot of creative ideas coming out of there, and we're excited to be able to provide this service to the globe.
Thanks, Jonathan. You guys certainly seem to be in the news every day with a new launch or something going on. So really excited to have you on and to dig into that a little bit more later in the panel.
Great.
So our final speaker rounding out the panel is Max Kaminetsky, who is the head of product at Loon. Over to you, Max.
Thank you, Diana. Thank you for that excellent introduction, for inviting me to the panel. Of course, thank you to the other panelists and to the audience. There are a lot of exciting things happening at Loon. I'm eager to talk about them. Our mission is to connect people everywhere. We started, for those who don't know, we started as a project within Google, within part of Google that's called X, which is known as the Moonshot Incubator within Google, but now we're an independent subsidiary within Alphabet. What we have done is we've redesigned the essential components of a cell tower so that they can be carried by a vehicle in the stratosphere. In our case, it's a balloon that's flying at 20 kilometers or about 65,000 feet above Earth. And this makes it possible for us to extend internet connectivity to places where it's very difficult to do so terrestrially. To do this, we work with mobile network operators to expand their coverage to parts of the world that are unserved or underserved. We try to supplement existing networks, and we also work with operators and other stakeholders to provide coverage after natural disasters. There's a lot of technology that Loon has had to develop to make this happen. There's still a lot that we have to develop to continue on our mission. But to date, we feel like we've achieved a lot. We've flown over 40 million kilometers in the stratosphere. We've flown thousands of vehicles with, at this point, vehicle flight times averaging 4 to 5 months. A lot of announcements we've had in the last few months. We announced that we're launching a network in Kenya with a mobile operator partner there, a great partner called Telecom Kenya that I'd love to talk about. We are also doing work in Mozambique, helping Vodafone there expand their network to places which otherwise are very difficult to connect. We announced a partnership with AT&T and with SoftBank. So I'm really looking forward to the discussion today, looking forward to learning from the other panelists and of course to the audience questions. Thank you.
Thank you, Max. So it sounds like you guys started in X, which was a moonshot factory. Now you've come a little bit closer to the Earth. Are you operating is at 20 or 30 kilometers off of the Earth's surface?
Yes, so we're flying at about 20 kilometers nominally above the Earth. So for reference, this is a lot closer than satellites. I mean, LEO orbits would typically start at 300 kilometers, and high-end GEO is, of course, 36,000 kilometers. So 20 kilometers is really a fantastic altitude for providing connectivity. It's much higher than any sort of terrestrial cell tower. So this enables us to provide much broader coverage, effectively very large macro cells if needed to cover broad areas. But at the same time, because we are so much lower than satellites, we are able to create a higher capacity density. And we're also able to connect directly to users' handsets. So one of the great advantages of the system is that as a user, there's really no equipment required beyond the handset, the LTE handset that you already have in your pocket. You connect to the same mobile operator network. And just like today, you don't know which tower you're connecting to. When you're connecting through the Loon network, you don't know that the tower you're connecting to happens to be flying at 20 kilometers and linking to other towers. In terms of how the system works overall, each of the balloons is about the size of a tennis court. We fill it up with lift gas, and then there's also a reservoir for air. The air is needed for us to control altitude, so that if we release the air, the balloon can rise. If we pump air into the system, the balloon will decrease its altitude. We have auto launchers. So what that means is that as opposed to launching the balloons manually, we have largely autonomous systems that we've built in Nevada and in Puerto Rico that enable us to launch balloons at a cadence of 30 minutes or so, with very few people required in the loop. This increases robustness, this increases safety, this enables us to get into operation very quickly. The way we get to the service area is by flying in the stratosphere. So literally flying with the wind. This is where a lot of the technology development has gone in. How do you take weather data? How do you fuse it with our own readings? How do you, as a result, plot a control strategy so that the only way to fly is to actually use the wind to propel you in the direction of interest. So we leverage wind currents in the stratosphere that may be going in different directions or with different speeds. And that's how we're able to navigate from the United States to Latin America or to Africa or to some other part of the world where we're trying to provide coverage, and how to stay in those places so that we can have a continuity of coverage. What's flying at on every balloon looks very much like a small satellite. So we have communication payloads. We have a multi-sector LTE payload. This is for access for users on the ground. And we have multiple backhaul payloads that allow us to connect to our own ground stations, as well as to form a mesh network in the sky. So the purpose of the mesh network is to reduce the number of ground stations. So literally with a single ground station, we can have a service area that may be thousands of kilometers away, and basically have the signal hop along from one balloon to the next balloon to the next balloon through this network in the sky. The system operates largely autonomously. So the navigation system for how we fly, the connectivity, the software-defined network that operates everything is largely autonomous. Well over 99% of all commands are autonomously determined by our software that's running in the cloud, and then sent to the vehicles to provide a continuity of coverage. There are three main product lines that we have. We focus on mobile network expansion. This is where we work with mobile operators to expand coverage to unserved and underserved areas. The examples I brought up, such as Telecom Kenya, Vodafone in Mozambique, are exactly those kind of deployments. The operator continues to own their customers, and we're merely a conduit for them to connect to them. The second product line is disaster preparedness. When cell networks on the ground or towers are damaged as a result of natural disasters, we have the ability to respond very quickly. Because our vehicles fly well above the weather and they're solar powered, that means our network is resilient, our network is flexible, and our network can be repositioned to respond very quickly. So that's the essence of a partnership that we announced recently with AT&T. And I'm happy to talk about that more if there are questions on that. The last one is aerospace network orchestration. So Loon has built what we believe to be the world's first autonomous production software-defined networking platform, specifically for aerospace systems. So we combine orbit propagation together with channel modeling, and that allows us to simultaneously solve for orchestration, network routing, and radio resource management. This is something we've been using in production for the Loon mesh network for a number of years, and we're currently starting to work with commercial customers in the satellite industry to enable them to similarly operate their networks with this kind of technology. So again, if there are questions about this, very happy to talk about it.
Thank you. And you gave a good segue to my next question by talking about some of the advantages of Loon over terrestrial networks. I'd love to hear from Ed and from Jonathan, what are some of the relative advantages of your specific technologies and infrastructure?
So let me jump in. So thanks, Max. I think that there's a lot of data there to unpack, and I know from my experience early on when I was at Qualcomm, we were providing some technology on the early testing with Loon, so when it was still part of Google. So congratulations on being out of that business and on your own. I think that there's been a lot of good evaluation and exchange. We've had some recent ones with your team in Africa, and it is a complementary platform. Frankly, there's a lot of things that we can't do terrestrially because of cost. We do build the lowest cost towers and infrastructure. We call it build to suit. So the operators approach us and we'll go out and build those towers in remote villages and areas. Some of them we've done to create digital villages in India and other markets where we can provide communication and educational opportunities as part of our foundation. So we're all about trying to provide that connectivity as well. On the commercial side, though, there are going to be cases where it's just not economic to make that investment. And so having, HAPs, as I call them, there's some that could be geostationary. This one happens to be moving, that there's going to be opportunities to interoperate those with the core network of the operators and use the operator spectrum to connect directly to phones. But we would work cooperatively on how to support that. Some of the use cases that we have ideas with would be to fly that trajectory, and then once you've established the demand on the ground, you can then more economically pinpoint where to build the towers on the ground, and then move the balloon is mobile, so it can move into different areas and territories over time, and you could use the spectrum terrestrially. So that's one thing. The other piece is for backhaul. So if we put in these remote sites, a lot of times we don't have the connectivity, so we have to solar power them. We have to find ways through satellite to provide backhaul, and through Loon we can provide some of that capability as well. So there's complementary aspects. There are going to be some overlaps for sure in cases where we'd like to build, but maybe this is cost-effective more terrestrially when there's demand concentrated, and when there's like limited demand but spread over wide areas. Then some of the HAPs and other technologies, including the work that Spacex and others are doing, those can also complement those locations. So I think it's part of let's say a continuum of platforms that we're starting to see, whereas there's just not one tool in the toolkit as we try to build out more of the Earth's surface area with connectivity for the internet.
Makes sense. Thank you. Jonathan?
I think Ed did a great job summarizing the relationship and the advantages. Without being too redundant, certainly the infrastructure equation is different for satellite or HAPs or for ground architectures. Like Ed mentioned, we think we're a great complement to the ground infrastructure. One of the unique things about what a LEO system and a HAP system can provide is continuity of a low latency system. And for the rollout of 5G and other technologies that I think we're going to talk about later, certainly keeping low latency systems will be paramount to the future. There's advantages for having a LEO network over a HAP network, depending on the use case. We're a global network, so where companies that have infrastructure deployed globally, having a resilient global and frankly a very secure network, having connectivity to all your sites globally is something that has resonated with a lot of potential enterprise customers. And the resiliency to natural disasters was another one that was brought up as well. So it's a great complement. We're looking at the architecture for Starlink and for LEO-based systems is not ideal for densely populated areas. It is more attuned to rural, unconnected or poorly connected communities, and that's where we're going to complement the telcos and the American towers. So I think there's a great symbiotic relationship.
Fantastic, thank you. Is there an industry that stands out as an early adopter, perhaps, of your solutions?
An early adopter.
Like a vertical?
Yeah.
Is that what you're saying?
Early adopter. Well, I can say that the reaction from the majority of the verticals have been, when can we get connectivity? We want it yesterday. And so part of it is making sure that our technology is ready to serve them. So nothing jumps out really as initial mover. Obviously, fixed assets are easier to deploy than mobile assets. And we're focused on initial deploy to direct to consumers to connect the unconnected. And we've already started that process with really exciting and life-changing results. And I think some of that will become more apparent over the next couple of weeks.
More announcements from you guys?
A lot going on.
I know, you certainly do have a lot going on. I want to talk a little bit about the different technologies and how they apply to smart cities and autonomous vehicles. You know, when we look at the full potential of smart cities, urban air mobility, like Hyundai is working on alongside others in the industry, and other future technologies, you know, we really need widely accessible 5G. Is it possible for us to reach the level of coverage needed for these new technologies to flourish, in particular in the mobility space, without leveraging space-based networks?
So let me take a shot at trying to touch on the whole 5G and terrestrial piece. So in the urban areas, clearly there's a lot of density and capacity demand. Obviously, with the current environment, some of the load is shifted to some of the suburban and other communities, and less mobility and even some, but that'll all revert. I think you have to look at what are the main objectives of what the network's trying to do. If it's being delivered terrestrially or being delivered from space, whether you call HAP space or LEOs or even GEOs. So a lot of that is continuity of service. So you're trying to provide extensions to areas where there isn't coverage. In the cities and a lot of the UAMs, UAVs, other types of platforms, there's quite a density of assets that can support the communications needs. But those same vehicles could go outside those areas. So if I look at a connected vehicle, CV, or even a connected autonomous vehicle, CAV, the people who build those platforms are trying to make decisions about connectivity and where it will be. Today, a lot of times for autonomous vehicle, they try to do everything on the platform, which makes the platform very expensive. If it's an EV, it's going to consume a lot of energy to perform and all the computations and sensors that are being fused to make navigation possible. So I think when you have reliable, and clearly the space-based solutions in the cities could offer a sort of a resiliency reliability mode, but it won't be the main capacity connection. In those environments, if you had, let's say, a shuttle in a city, you could depend on the infrastructure with some level of redundancy for the most part. As you go to the outlying areas, the question for the manufacturer of those platforms is, will you then revert or depend on connectivity for any part of your subsystem? So the main safety platform people want to have, on the platform, all the computation and sensoring to support that. But there's a lot of infotainment and other subsystems that might need connectivity. So you're going to see that transition and understanding that once, let's say, a Starlink and other systems are available over the wide area, the people who make those platforms are going to say, yeah, I have connectivity everywhere. How does that change what I do on those platforms from an overall system design? And I think terrestrially 5G can provide that capacity. There's going to be a ton of spectrum. We just saw even last week or the other week, another 100 megahertz that NTIA has released and the FCC will auction. We've got the CBRS or the PAL auctions occurring as we speak. We also have this C-band satellite piece that's going to be started later this year. So there'll be a ton of spectrum. There'll be a lot of new capital investment. And I think terrestrially in the cities, that capacity should support most of the sensor and requirements and the dependencies on those systems the manufacturers of those platforms should be comfortable with. But if that platform has got to be mobile outside of those core city areas, then you have to think about how you interact with these other, let's call it space-based solutions. And I think that's what I would want to do. If I built a car, I'd have to know that that car can be used pretty much anywhere. You can't control unless the vehicle is limited to certain geography or geofence. It could find its way into remote areas. So it's all complementary at a system level. We have to believe that the platforms are in place. Once they're in place, then people could start to be innovative on how to use the connectivity to create better autonomy at more efficient power consumption for what is essentially electronic vehicles.
Thank you. Any thoughts from Phil or anyone else on the panel on this one?
No, I thought Ed did a good job again.
All right, so how can space-based networks, near space assets, and traditional cell towers complement each other to build a more safe and robust system for autonomous vehicles on the ground as well as in the air?
Maybe I can take a crack at this. I think what Ed said was exactly right. At the end of the day, when you look at population density around the world, there's orders of magnitude difference between the densest areas versus the least dense areas. And so that means that there's not going to be one solution that's sort of a one size fits all for everything. Multiple solutions have to exist in tandem. In dense urban areas, this is where you're going to be deploying picocells and femtocells and technologies where maybe you're going to have effectively a cell tower on every single street corner. And that's probably what you have to do if you're thinking about something like 26 gigahertz or 28 gigahertz for 5G. That's not what you're going to do as you start moving to more suburban or rural areas, because the economics probably will not support that. So that's when you start thinking about macro cells. And the question is, how do you create those macro cells? This is where towers, taller towers come in. This is where maybe providing satellite-based or HAPS-based backhaul to those towers starts making sense. This is where Loon, with our 20-kilometer tall tower, starts making a lot of sense, because you don't need security for that tower. You don't need diesel generator backup. You don't need a lot of the other encumbrances that you would need to have. But at the same time, you need to provide connectivity in the way people and these vehicles actually want to consume it. So that means you also need to think about the terminal. The simplest, smallest terminals we have today are NB-IoT solutions, are the other 3GPP compliant solutions. So that's something we're thinking about very heavily. We're thinking about and we're participating in 3GPP release 17 discussions. How do you unify terrestrial and non-terrestrial networks? So there's a working track called NTN, non-terrestrial networks, that we think is very interesting. Similarly, how do you use the same spectrum for providing, in a very efficient way, for providing both access and backhaul? And that's also an effort called integrated access and backhaul within 3GPP that we think about. Maybe the last piece, you need to have seamless coverage. So that means that all these networks, in a way, have to play together. So what's going to be a solution? What's going to be a sort of the network orchestration element that allows a consumer or a autonomous device to roam from one operator's network to another operator's network to a satellite network like Starlink? These are the kind of things that I think need to be thought about, because to the extent that we can make it seamless, to the extent that we can make it easy for customers and enterprises to use these technologies, that's the best way to maximize utilization and to make this very attractive.
Great, thank you. Let's turn things over to Phil. I want to hear a bit more about your background. After spending nearly 20 years in the private sector, now your time at NASA, can you talk a bit about your role in developing public-private partnerships and how critical they are in developing our future networks?
Yeah, when I look at NASA's communications capabilities today and what the market looks like, things are radically different from when we started the TDRS satellite system in the early 1980s. I think back then there were 6 commercial satellites and had about 200 transponders in orbit in the early 80s. And today we have roughly 500 commercial satellites that represent probably 6,000 transponders, and the data that can go through the transponder is much more robust than it was before. So we established the TDRS network in those early 80s, and we just launched the last one several years ago, and we're not going to be doing that anymore. The situation today could not be more different. We now want to be one of many users. That's sort of the mantra that we say within NASA, not just within telecommunications, but also in launch and commercial human spaceflight. we mentioned getting Bob and Doug back safely. Those were our two astronauts that SpaceX took up to the International Space Station. So what we're doing there is we're not relying on government systems anymore. The shuttle was the system to take people to low Earth orbit, and now we're relying on SpaceX with their Dragon capsule, and soon Boeing with their Starliner capsule. So same thing with telecommunications. We are not going to build another TDRS network. We don't think we're even going to build another TDRS satellite. We are going to let that graciously degrade over time, and we were going to be incrementally leveraging more commercial satellite communications capabilities as we go forward. So we need to figure out a partnership approach. Diana mentioned that very well, that works for the government and works for industry. I think there's a lot of capabilities that we can just use as they are today, but I think NASA has some unique requirements for some of our satellite systems that might require a slight tweak or a slight change in either the satellite comm package or maybe the overall architecture so that you can support our needs. So we are now doing this, what we call the Communication Services Program. We hope to fund some development and demonstration projects so that industry can demonstrate that they can satisfy some of these unique NASA requirements moving forward. So I think that's what we are going to see from NASA in the next few years. And then as we see those demonstrations be successful, NASA hopes to transition just to be a services user, where we say, hey, these are our requirements. We don't fund any development. We just leverage the capabilities that are out there today. And we think this is going to be beneficial for a lot of reasons. Obviously, number one is lower costs. We don't want to have to maintain the kind of infrastructure that we've had to maintain in the past. Not only the TDRS network, but also the ground infrastructure as well. I think roughly half a dozen new ground network providers have entered the market just within the last 5 years. We want to leverage that moving forward so that we don't have a large network of government-owned or operated ground stations. So I think you're going to see a lot more of that moving forward. We just started this communication services program last year, and so you'll be hearing some more about that. But I think what you said is really important, Diana, in that the partners, it's in this sort of early phase when we're doing this demonstration and development projects, that is really going to be a partnership. We want the industry providers to have skin in the game. We're going to also provide some funding as well to meet our unique requirements, and then transition to be just one of many users. We're just going to be a customer, hopefully like any other customer that you might have. We're probably going to have some unique security requirements, but other than that, we're trying to minimize any sort of unique capability that the industry might need to satisfy our requirements.
Makes sense. Thank you. Jonathan, with the success of the Falcon 9 rocket launch that most of the world has had a chance to see now, you guys have added a lot more satellites in space to the broadband fleet. Can you tell us roughly how many satellites do you have up there? Are they all active? What does that look like?
Sure, and I was hoping to get to a more definitive answer to you. So we've launched 655 satellites. That includes the original first two Tintin ones that we had done, and some of them have been deorbited, but the vast majority are operational. One of the key things about the technology, and people think about satellites in space as being a very long-term investment. It takes years to build the satellites. They have to last 10 to 15 years on orbit. From an architecture standpoint, we are taking a very different approach, and we're going to be challenging even the ground infrastructure folks to iterate on their designs at a much higher rate. So we're already looking at plans for our next generation satellites, and I know that was one of the questions from the audience. So once the 1,440 satellites are put up, that's not the end, right? And we'll continue to iterate and actually deorbit the satellites of the older generation. And the fact that we're building 6 satellites a day and launching every 2 weeks, we can deploy new architectures much more rapidly than traditional aerospace, and much more rapidly maybe even than some of the terrestrial folks can do it. So certainly we're going to challenge them to get newer technology, more efficient technology on orbit quicker and to the customers quicker. So we're going to get the efficiencies of cost and new technology deployed very rapidly.
Thank you, Jonathan. One of the things that caught my eye on Twitter the other day was the name of the drone ship that you guys used for the Falcon 9 launch. It's called, Of Course I Still Love You. Very interesting name. I know its predecessor was Just Read the Instructions. Can you tell us a bit about how those names came about and the evolution in tone?
Sure. Well, not surprisingly, SpaceX is full of space geeks like myself and the majority of people here. So for those who don't know, like our Falcon 9 program actually came from Star Wars, which was the Millennium Falcon, which was Han Solo's ship. We took that name, dropped Millennium, kept Falcon. 9 is 9 engines on the first stage. So along the same lines, we're drawing from our sci-fi interest. Of Course I Still Love You and Just Read the Instructions are, we've gotten a lot of comments on this because they're very unique names. It's based upon a novel series by Ian Banks called Culture, and it takes place in the future where AI is prevalent, and two of the drone in the series there are autonomous drone ships, and they get. And the first two that get named are, Of Course I Still Love You and Just Read the Instructions. But my understanding is that the AI in the future, they name themselves. Not sure if that's 100% correct, but and these two autonomous drone ships, the AI, they name themselves at birth. Just Read the Instructions and Of Course I Still Love You. But yeah, we've gotten a lot of interest. Certainly it's catchy. My kids say it all the time. So yeah, that was the nature of it.
Great, thank you. Max, can you tell us a bit more about the launch of the 35 balloons that you recently deployed in Kenya?
Yes, absolutely. This is really exciting for us. We've been working on this technology for some time. Loon started as I mentioned, as a project within Google X back in 2012, 2013. And in the early days, I mean, the first experiment literally was, can we launch a router on a weather balloon, and can we get something to happen? And the answer was yes, it does fly. Yes, you're able to get a connection to it, but it lasts for maybe an hour or two. So not proof of life, but not really a business you can build out of it, and not really a service you can provide to anybody. Fast forward a number of years, we started building networks and operating at scale, really. And the first tests of our system were back a few years ago when there were massive floods in Peru, and there was a Hurricane Maria, that hit Puerto Rico. So these are horrible natural disasters. We happen to be already starting up operations in both of those places, and we had a choice. In Peru, in particular, we were about to go into alpha trials with about 25 hand-picked users. So the choice was, do we continue with alpha trials, or do we just turn on the network, because there was a tremendous demand. The terrestrial network was wiped out. We decided to turn the network on and see what happens. And we ended up connecting hundreds of thousands of users during these times. That really was sort of the battle test for Loon. Do the vehicles fly long enough? Can they stay in the area? Can they provide continuous connectivity? Can they ultimately help people? The deployment in Kenya is different from the perspective that it's not a response to a natural disaster. It's a long-term deployment, working together with our customer, Telecom Kenya. We identified a part of the country that was underconnected, where they did not have a good network, a 4G network in place. but where it was clear that there was a lot of demand for connectivity from the people who live there. So that's a network that we deployed over there. It just launched. It just went live very recently. We're having some really good results. We are very happy with our partnership with Telecom Kenya, and looking forward to rolling this out in other places. I already mentioned we're working with Vodafone in Mozambique. Again, a similar scenario where there's a part of the country that's underconnected. And in general, we think that there are a lot of opportunities in Africa, in Latin America, in Asia, and in many parts of the world to provide connectivity to people. Approximately 50% of the world's population is offline, meaning they do not use the internet. And there are many barriers to this, but access to data capable networks is one of them. And so that's what we're trying to work on.
Fantastic, thank you. We're going to start taking some audience questions in here and there. So the first one that we have is, what orchestration mechanism can allow a user to roam from a terrestrial network to Loon and then to Starlink?
So let me just take a shot at the high level view of that, then these guys could probably speak to that. So first is there are different types of networks, they have different types of terminals. And to the extent that you're using a device that either has to be multi-band or multi-capable in terms of modem, depending on the underlying technology. So, you know, if you want to use, let's say, classic cellular modems, to Max's point, the lower app is consistent with that. If you're looking at Spacex, you're looking at a fixed user terminal today that could be mobile in the future. I believe that different bands and different capabilities as far as the modem. Now they could modify that and also extend some of the capabilities there, but those are all part of the equation. If I had a subscription today in a mobile network, I have what's called a home subscription center, like HSS, that sets up my authentication and allows me access. Both for all the Gs have had various, you know, improved, let's say, sophistication on security and authentication of how do you access a network and whether the base station is legit. In the case of the core network, that's where that's housed. In the case of the radio network and the client device, you have to go through an exchange protocol to be able to authenticate that you're allowed to access that network. Where those pieces could come together is where you have mobility in, let's say, in a Loon environment, to be able to say that that subscription sees the same mobile network ID for authentication when you acquire and synchronize your mobile device to whatever radio you're seeing. That can allow you to access that particular network, whether it's a HAP or whether it's terrestrial. Those are the types of things that happen. Now, if you take an IoT device, there are folks looking at either LEOs or MEOs or even other systems that say I have what was talked about earlier, like a narrowband IoT device, call it a sensor. I put it in a shipping container in LA and I'm shipping it to Hong Kong. So terrestrially, I might be on AT&T or Verizon in LA, and that's sort of managing their, let's say, the temperature in a refrigerated container as the ship leaves port and spends a week or so crossing the ocean and then gets into Hong Kong. You know, how is that now captured? So the satellite needs to take over at some point. There's a handoff, sensors reporting back. The data is being collected by whoever the owner is of that service. And then when it ends up in Hong Kong and starts to go terrestrial again, it'll get tracked by a local network. So the authentication has to be between the mobile terrestrial provider, the roaming relationship with Hong Kong, and then whoever is the service provider from space that's providing that connectivity during the time where it's on the ocean. So there is a back-end system that allows that to happen today. And it's called, there's roaming and other relationships that are sorted out economically as to who pays who and who the subscription is with that originated that device, so that it's properly authenticated on the network. Those are sort of fundamental mobility capabilities that are based on the standards that we all enjoy today in say 4G and 5G.
Perfect, thank you. Let's talk a little bit about global competition and regulatory frameworks. In the US, are we allocating enough resources towards developing space-based networks? Are any other countries in the lead? And if so, what does that mean for our role here domestically as a leader in aerospace and space travel?
I can take an initial stab from the SpaceX point of view. I certainly believe that the United States is in the lead at the moment, but being in the lead, our competition is fierce. So you always have to be careful of who's behind you. We know that the United Kingdom, Canada, and China have also invested in low Earth orbit satellite constellations and emerging technologies. And so the U.S. has done a lot to kind of support this low Earth orbit network and support this industry, which I think has clearly put us as a front runner. But we have a bunch of big decisions in front of us from the FCC standpoint, and they've been a great supporter. But there are three main things that we see that are ahead of us. One, as the U.S. government evaluates technologies, we are a strong believer that the best technology should win, independent of the technology. So a technology neutral approach when we're looking at government subsidies, et cetera, the best technology should win. The second piece that could potentially stifle us is the fact that we have this next generation satellite system, and where the FCC is looking at the spectrum and how to handle it, giving away spectrum that is key to us, to speculators such as the 12 gigahertz spectrum is something that we want to be extremely careful of. And the other thing that the U.S. government and other governments around the world, I think, have to come together is how do we, on the satellite platforms, how do we manage orbital debris? So we need an aggressive but realistic approach to handling the orbital debris issue that is consistent, but allows us to be competitive globally and doesn't stifle our U.S. licensed systems to be able to operate economically. So yeah, kind of in summary, the U.S. is doing a lot, but we got to continue to be vigilant to making sure that the best technology is at the forefront.
Yeah, and we've seen, I think just last week or so, the White House just announced plans to make some of Pentagon's spectrum available to telecom companies in the United States so that we could increase competitiveness in 5G expansion. Ed, I don't know if you'd like to comment on that move.
Sure. So on the regulatory side, a couple of things. So there's the RDOF and the U.S. service funds that there'll be some, I think, reverse auction and some decisions made on how to support that. And I'm assuming lots of different players, both from fiber and obviously the terrestrial players are going to support that. And then there's this 5G push. The other part of it is around O-RAN, opening the network, making it more cloud-based and virtualizing it. And that's going to help, competitiveness, because the total solution set on telecom had reduced down to a few handful of OEMs. And a lot of those were concentrated too in other countries. So what we're looking at in terms of the US and 5G is the world had consolidated around what they call mid-band spectrum, sub 6 gigahertz in the standards world, but 3.5 as generally the band where the magic of 5G will really happen, right? There's a layer cake of spectrum that's being delivered to the market today. Earlier mentioned the high band, which is the millimeter wave, very dense, small cell locations in cities and urban areas, some in venue. We have the low bands, like the traditional cellular, early 1G, 800 megahertz, 700 megahertz. Those bands are being used for wide area coverage. And then the mid band is really where you can get the combination of wider band spectrum, the leverage of the macro tower infrastructure, the high gain antennas that can be positioned. And we were in the US, frankly, behind in being able to release that spectrum compared to other markets around the world. And what we have had is the Navy had operated in a portion of the 3.5. There was other fixed spectrum being used at the upper end of 3.5. That became part of 150 megahertz they call the CBRS band. It's got a 3-tiered structure. Navy's primary, and there's a SAS controller. So it's a little more complicated about who can place base stations. That went commercial last year in the unlicensed portion, and the PAL auction is going on as we speak, as I mentioned earlier. That's going to open up a sort of a first phase, which is 4G, and then eventually 5G. The C-band spectrum, which was the existing C-band satellite operators, Intelsat, SES, and others, paring back some of that, moving some of that traffic terrestrially for video, is going to free up 280 megahertz of spectrum of that 500, so all the way up to 4 gig. That's going to really be a key part. That'll be auctioned starting later this year. And this NTIA spectrum, DoD and Pentagon, that's been on the discussion board for a while, and it's great to see that the government has moved to free that up. And I've seen a lot of really interesting things happen very quickly in government around this mid-band, because I think the importance of 5G and having to get that additional spectrum out and building out the coverage and capacity that we believe will transform certain industries from an enterprise perspective. That's at the heart of it. And I think having that extra 100 megahertz will help, give operators new options about how to leverage that spectrum for the deployment of 5G. So you always have the high band, and those are some of the things we're doing, but it's very limited coverage. You have the low band where you get coverage, but you don't really get the capacity. And sort of the Goldilocks, as some people call it, is in the middle, where we can now take more advanced radio technologies and leverage the macro tower infrastructure to support a wide area, high capacity solution with low latency for 5G.
Thank you. Yeah, it's definitely clear we need more access to 5G spectrum, especially for new mobility solutions. Phil, I'd like to ask you, on the topic of 5G, as we see more and more become available, should we be concerned with any spectrum interfering with weather forecasting or any other necessary functions?
Yeah, that's a great question. That is a key concern within the administration and within NASA. NASA operates some very key science systems in frequency bands that are adjacent to those identified for 5G. Specifically, there's a band reserved for passive remote sensing, and that represents decades of development and billions of dollars in taxpayer investment. So we're committed to finding a good balance between the development of 5G technologies and also continuing to support the data acquisition used for weather prediction and public safety. So I think we've been sort of aggressively working with other members of the federal science community. That includes NOAA, NTIA, FCC, maybe even the State Department, to making sure that we do have a good balance. I think some of those efforts are kind of in their infancy. The newly identified 5G frequencies were really just established at the last WRC. So we want to, I think NASA's standpoint, just want to find a good balance. I will say that early and continued engagement at the technical level with sound engineering can be successful. I've got some notes here. At the WRC 15, NASA led some studies that demonstrated that 5G technologies would be incompatible with some of the NASA operations in the 2025 and 2110 megahertz and 2200 and 2290 megahertz bands. So as a result, both of those bands were removed from consideration for future 5G deployment. But on the flip side, at the same conference, we had some studies that showed NASA operations in the 1400 to 1427 megahertz bands were compatible with the use of 5G operations on the adjacent bands, and those were approved. So that's the message. We can get in there, we can show if you have sound engineering. We definitely recognize not only the commercial capability, but also just the overall services that can be provided by 5G. And we just need to have a lot of dialogue and ensure that we can do that in a way that doesn't jeopardize some of our existing weather spectrum and science spectrum data.
One point on that too, Diana, that I'd share is that as you move to different platforms in space, the interference, issues become more, let's say, critical, because if you're sharing spectrum or you're trying to build, you reuse the same spectrum, you've got to make sure that you're handling the signal to noise, the sort of impairments that can come from that particular system is different, right, than terrestrially. And so a lot of these things do interrelate, and we have to make sure that there's proper bands and proper protections for the existing users, but also opening up this new spectrum for innovation, right? So this is a combination of issues that have to be solved.
So in addition to interference concerns, there are also concerns about space collisions between satellites and other debris with the proliferation of 5G satellites. So Jonathan, as our autonomous systems begin to rely on 5G satellites, the safety of these devices are obviously going to be very critical. Can you tell us what work is being done currently to minimize the hazard of space collisions?
Sure. And this is something that's near and dear to our hearts. Keeping the environment in which the fundamental essence of our Starlink business is based upon keeping it clean and safe is our priority. And so there's a number of things that we've done along the way to ensure that we're taking a smart approach. You know, the first one is simply the altitude. From a physics standpoint, we lowered our architecture from a higher altitude LEO constellation to a lower altitude LEO constellation at 550 kilometers. That's if you do have an issue with the satellite, the deorbit time, you don't want it to be up there for tens to hundreds of years. You want it to deorbit on the order of months. And lowering the altitude does that. The first thing that we actually do is when we launch the satellites, we launch them into a much lower orbit, and we do a system checkout at a lower orbit. If any of the satellites are not 100%, they get deorbited on the matter of weeks. Once we get the thumbs up on the satellites, then we orbit race them to their operational altitude. And so on top of that, that's for step one. And when they're operational and flying, each one of the satellites is autonomous. If you think about operating thousands of satellites, you can't be commanding them manually. And so we're very open with our positioning data of the satellites amongst the community. So there's a lot of conjunction analysis that gets done. And you know, conjunctions or potential conjunctions happen all the time in space, and making sure that you're aware of it ahead of time. The great thing about orbital mechanics and physics is that it's predictable, and you know, within some uncertainties, so you can actually see what's going to happen before it happens and avoid it. So yeah, orbital debris, and that's just for our constellation. And I think one of the fundamentals to keeping safe space a clean, safe place to operate is addressing those standards globally for other folks that put in satellites into that orbit. You connected this also to safety on the ground. I think one of the unique things about having a larger constellation is the resiliency of being a network of multiple satellites. If you lose a single satellite, the network redistributes and you don't lose connectivity. And so as you get into the autonomous future that you were describing, that is something that you're going to want. You're not going to want to rely on a single node, but multiple nodes. And like Ed highlighted earlier, it's not going to be just necessarily one architecture, but probably getting data from multiple architectures and triaging it to make sure you have the right information to safely operate on the ground.
Thank you.
Yeah.
Phil, my next question is for you. NASA estimates that deep space communications capability will need to grow by nearly a factor of 10 each year of each of the next 3 decades. Do you think the telecom industry is on pace to meet those requirements? And if not, what more needs to be done?
Yeah, so that's a great question. It seems like, you know, the telecom industry and users are just like teenagers with their cell phones. You just can't ever get enough, right? I actually remember a day when I tried to meter my daughter's cell phone use and their text messages before everybody just went unlimited. It seems quaint now that I could actually think about doing that for a short period of time. But then, you know, now we've all got unlimited data. So keeping pace with the demand is something that is obviously going to be a challenge, I think, going forward. We're we're obviously looking at new technologies and new capabilities, higher radio frequencies, obviously the use of more K-band, S-band, X-bands, advanced modulation, coding techniques, arraying multiple ground antennas to form these large virtual apertures. Obviously, one thing that NASA's been interested in is optical communications. We're funding some technology development area in that area. And we're also focused on and funding some studies on just, this whole concept of internet in space and disruptive tolerant networking to automate the data flow. I think all these things are going to have to get in the mix, right? So that the commercial industry can keep pace with demand going forward. And I like the approach now of just, throwing all these things into the hopper, and the market will ultimately figure out which one I think is going to succeed and which one of the companies have the best business strategy to address the growing demand that we see.
Great, thank you.
I would just put a data point out there, Diana. In India today, you're seeing 10 gigabytes a month, for hundreds of millions of consumers and at least one operator, right? So and the price point per month is like $2 US. So you have economics that really drive this as to which area of the system and which frequency will ultimately get the economies of scale and the cost of the components. And these are things that really, I think, ultimately will find the right, let's call it a market-based solution between what's done for a wide area where it may be, I need to spend more money because there's no other way, and what can be done, let's say in the cities where we have this spectrum, we can unleash new bands at different frequencies, higher frequencies, even 6G is talking about terahertz, capabilities. And these are all things that are in the hopper to satisfy demand as we move forward to, say 2030, where you have, maybe different types of mobility platforms in cities flying through the skies, providing transport, right, differently than we do terrestrially. So I think there's always engineering solutions if we can get the spectrum and regulatory environment to support it, and then the economics will follow the best sort of economies of scale for that particular use case. So I don't think anybody should be worried that we can't find enough bandwidth and let's say capacity for these opportunities.
Great, thank you. And we've got another audience question. I think this one's probably for Jonathan and Phil. The satellite innovations sound amazing. How do you respond to concerns that the proliferation of many more satellites will negatively impact ground-based astronomy?
Yeah, so I can address that, and then Phil, you can follow up where I missed off. So this is obviously something that has come to public's attention. We actually been working very closely with the astronomy community since we launched our first batch of Starlink satellites when the concern was first approached. So again, the beauty of being vertically integrated is that we very quickly could iterate and determine how best to deploy a constellation that doesn't affect the astronomical community. So we've looked at, I think we call it dark sat, where we increase or decrease the reflectivity. We've added different shields in order to make it less obstructive to the astronomers. So we're actively trying to make this right. Again, as space lovers and space geeks, and we don't want to affect the ability to study the stars. So I think our interests are aligned in trying to find a common solution. And it's been very positive, the reactions that we've gotten with our outreach. So we appreciate their concerns.
Great, thank you. Phil, anything to add there?
No, I don't think so. I think that covers it.
Sounds good. Max, we've got an audience question for you. Hydrogen, helium, what's in those balloons and why?
Good question. We use helium today. We have looked at hydrogen. We know some others have used hydrogen, may continue to use hydrogen. It is possible to use hydrogen in a safe manner. We believe so, and we've done the technical analysis. We believe that demonstrates that. Helium is a great lift gas. We do need some sort of a lift gas to be able to fly. We don't have a rocket engine strapped onto the balloons. And we're able to use helium in a fairly sustainable way. We use it quite sparingly. The balloons fly today for, on average, 4 to 5 months. Our longest flight was over 300 days. So when you compare that to sort of the early day experiments that I was telling you about, where we were flying for 2 hours, and that was considered a success, it's quite remarkable how far we have come. I did want to go back to something that that Jonathan, I believe, was talking about, and that's sort of this design iteration. This is really important for us as well. The fact that our vehicles are only designed to last in stratosphere for hundreds of days, as opposed to for many years at a time, enables us to fly new technologies very rapidly. So the time from sort of conceptualization of a design to when it's actually flying on a production vehicle is quite short. So when we think about introducing technologies like 5G, as an example, this is something that I would say is in the near-term horizon, as opposed to far off in the future. This is one of the advantages of stratospheric vehicles. This is also obviously an advantage of LEO type systems. The economics for GEO are quite different, where it's difficult to design a satellite that would last only a few years and still have that system be profitable.
Great, thank you. Jonathan, we've got a question for you. You mentioned 1,044 satellites for the first generation Starlink. SpaceX has filed spectrum allocation applications for about 42,000 satellites. Can you comment on the planned constellation size of future generations and the role your dedicated rideshare program will play in these future deployments?
Sure. I think the correction there was, it's 1,440 satellites. So I apologize if I misspoke earlier. And with 1,440 satellites, that's when we get 24/7 global coverage. And the plan is to not stop there, is that we'll continue to launch, and with each launch we can provide more and more capacity. And I think, as Phil was mentioning, is like there's never enough capacity. You can't limit what your kids want to watch and what everyone wants to consume. So we'll continue to densify the network. We are also looking at other versions, other generations of our Starlink constellation that's already in design and development. Not going to comment on timing of those and to what extent those will reach the 42,000 that we've filed for. But certainly, I think the future will warrant more and more bandwidth, and leveraging that with the new technologies is something that we're going to do. The second part of the question about rideshare, as we bring Starship online. So rideshare is a program near and dear to my heart, having done the launch for the small sats to start with. So I think we're enabling companies to design the future capabilities of space, and that's something that the company has been supporting and will continue to support. I don't see a change in that. Maybe we'll roll out some additional capabilities in order to allow folks to test out their hardware. Yeah, but so I started to say Starship is coming online, hopefully in the very near future, and that capacity is virtually unlimited from a lift capability to LEO. The intent, while we've broken the mold on the number of launches a year, I think we're gonna try to outdo that with Starship, with much lower cost, much more frequent launches of Starship, which will continue the rideshare capabilities for future customers.
Awesome, thank you. I've got a general question for all of the panelists. Do these technologies that you're using rely on a global supply chain? And if so, are you concerned about recent policy moves in the US to limit or restrict Chinese components in certain technologies? Is a country of origin approach based on where something is made an effective way to solve security challenges? We'll open it up to anyone to weigh in. This has been an issue in the commercial drone space quite a bit over the last couple of years, and we're starting to see it in other technologies that are deemed critical to national defense as well. So there's certainly a trend. My personal perspective is that we should have access to a global supply chain and have the ability to use components from different countries, so long as they meet a certain security standard that should be a global standard developed by an international organization that can also be audited by end users. Would love to hear any additional thoughts on this from any of the panelists. No takers. Okay. So Max, you guys have had some recent announcements with AT&T on a partnership on disaster response and some other areas. Can you talk a little bit about that partnership and what you've been doing with AT&T?
Yes, so we're really excited about our work with AT&T, and there's maybe a couple of things here. The first is disaster preparedness and response. When there is a natural disaster, and if it is something where the terrestrial network is affected, the ability to respond quickly is extremely important. So I already talked about some things we can do and already do today to enable that. And so those are things like autonomous launching systems, the ability to dispatch vehicles very quickly, to navigate to a specific area, to stay in that area, to provide broad area coverage, effectively macro cells from 20 kilometers or 65,000 feet. The ability to fly above the weather, solar power, so all the kind of things that you need when the network on the ground has been destroyed. There are other things you need to actually be able to provide connectivity to users at that time, and that's integration with the operator's core network. So Ed was talking about this as well. The core network that a mobile operator uses is quite complex. And the way it typically is deployed today, it relies on a constant connectivity to towers. And certainly it does not assume that towers are moving. So we have developed technology that allows us to integrate with operator core networks. And we do this quite efficiently. But still, it may take 1 to 2 months of deployment and careful testing to make sure everything's ready to go. That's the kind of time you do not have when a natural disaster has just hit. And there are hundreds of mobile operators around the world, and it's very difficult to predict what's going to happen where and when in advance. This is why the partnership with AT&T is so critical to us. AT&T already has relationships with hundreds of operators in hundreds of countries, or well over 100 countries around the world. And what that means is we're able to integrate once with AT&T's network, and through that integration, be able to provide services to operators wherever the disaster may have hit. So that saves a lot of time. That enables us to serve multiple operators simultaneously if that's needed. The other thing is that I wanted to go back to something that was being talked about before, which is just 5G. 5G is very interesting because it has the potential to bring massively fast data rates to consumers. But to do that is extremely difficult. You need to move to higher frequency spectrum because that's where you have such broad bandwidths that are available. But when you do that, deploying such a network and operating such a network becomes really hard. So signals don't propagate as far. interference becomes a major challenge. Even weather can affect high frequency radio signals. So there's two things that Loon is doing that we think can help. The first is if you think about deploying a high frequency network, and you think about deploying this in a more suburban or rural area, putting a cell tower in every corner is just not going to work. Economically, it's just not going to work. So having the ability to deploy a macro cell, and in our case, a macro cell from the stratosphere, is something that is quite interesting, and we're seeing a lot of demand for mobile operators for that. The second is from the operation of 5G networks. It's becoming quite complex. There are new standards that are being developed. These are being organizations like 3GPP, organizations like ONF, ORAN is putting together standards. We think ultimately you need to have something where technologies like terrestrial, stratosphere, and satellite are unified. We think we have a software-defined network that can actually do that. And so we're very excited to be partnering with satellite operators, with terrestrial operators, and even with other stratospheric operators like HAPSMobile to bring this to life.
Thank you. Jonathan, we've got an audience question for you. Do you plan to work with any orbital debris removal services in the future for operational satellites that may experience anomalies?
Is this coming from someone who owns an orbital debris management company, most likely?
Well, they didn't name a couple of companies here.
Certainly not opposed to it if it's needed. To date, we haven't needed it, and so happy to explore what makes sense to keep space clean.
Thank you. Max, thanks for sharing insight into the AT&T partnership. Can you also tell us a little bit about SoftBank's investment last year? I believe HAPSMobile, their subsidiary, invested about $125 million into Loon. Can you tell us how the companies have been working together since that investment?
Yes, absolutely. So we are really well aligned with SoftBank, and that's why we decided to partner with them, because we together with them, we believe that there's a future where various types of high altitude systems, such as balloons, such as the solar planes that they're developing, will be working together to create connectivity for people on the ground. But this can only happen if these types of systems are compatible. So you need to be able to create a seamless network. Otherwise, the user experience is just is not going to be there. So there's two things we can talk about publicly today. The first is we have adapted our stratospheric communication payload for operation on SoftBank's vehicles. So they have a high altitude solar plane that they're developing called Sunglider. And it flies at a similar altitude to our balloons, but it has, let's say, fairly different properties in terms of how it operates. In our case, we have flight-proven communication systems that have flown on thousands of vehicles at this point. There's some additional design and engineering work we have to do. We're happy at this point to be able to say that these systems work on HAPSMobile vehicles, and they're designed to work in a way where you can, in fact, create a single network. So as an example, you can mesh a HAPSMobile vehicle together with the rest of the Loon network. The second thing is that we think that the HAPS industry will win when we all work together. So when we all work together on standardization, when we all work together in our engagement with regulators around the world, regulators for aviation as well as for telecom. So together with HAPSMobile and a number of other companies, we launched a new organization called HAPS Alliance to promote this kind of standardization, engagement with regulators, and commercialization HAPS platforms. So HAPS Mobile is a founding member together with Loon. We are very excited that a number of other companies across aerospace and terrestrial networks have decided to join us. So great companies like Airbus, Nokia, Intelsat, AT&T, Deutsche Telekom, Airtel, AeroVironment. The goal is to have these kind of like-minded companies working together, amplifying our voices, and making HAPS mainstream. So we really do think that this sort of signifies the arrival of HAPS onto the main stage.
Thank you. Ed, speaking of HAPS, how do you see solutions like that fitting into your vision of a telecom network of the future? And are you considering different types of technologies or infrastructure for different geographies?
Yeah, so I think, as Max said, HAPS have a role. They've been primarily disaster recovery and limited coverage areas. In terms of mainstream capacity, it's not going to be what we do terrestrially. So there's a complement there. And I think also the LEOs, as they come online with Starlink's satellites, I think there's an opportunity to further extend that to some of the fixed, and then how you can extend coverage and capacity to new areas, right? So we look at this as a complementary ongoing evolution to newer technologies that can provide more efficient opportunities where appropriate, right? So first of all, we didn't talk about in-building. So when I look at macro towers are complemented by small cells and by in-building systems. So the way that small cells and in-building systems complement the wide area coverage of macro, I think HAPS and LEOs will provide that same level of capability as they extend connectivity into areas for coverage. It's some of the capacity numbers that I mentioned that we see terrestrially today in markets like India, even in the US, where there's unlimited plans, the demand will continue to go. And you really need to look at the economics of these systems. A lot of them in the past have struggled because the cost per bit and the way those systems get put together and the operating costs are not as, let's say, attractive, but improvements will continue to happen. So we'll look at those. We'll work and partner with folks, as I mentioned earlier, how we can leverage HAPS to find where coverage is needed and where the capacity demands are, and we can fill in with terrestrial, or those can stay permanent depending on what the overall needs are from a coverage or a demand standpoint. So it's definitely adds new tools to the toolkit. We're about multi-tenancy and trying to make sure that there are efficient solutions that different operators can use with their spectrum. And we're excited. I'm excited about all the things that are going on. There are other people doing geostationary HAPS. There are people doing, direct LEO to devices. Those are newer players coming in the market, and I'm tracking all of that, and we're trying to figure out how those fit into our global infrastructure business.
Great, thank you, Ed. We've got just a couple minutes left. I have one quick one for Jonathan, and then we'll do a go around with final thoughts and key takeaways. Jonathan, can you tell us if the board Elon Musk Twitter account is run by Elon himself?
I had no idea.
I won't even blame that one on the audience. I wrote it down myself because it's the first time I've got to be on a panel with someone from SpaceX.
Yeah.
All right, cool, thank you. So let's do a go around on final thoughts and key takeaways in our last minute and a half. Phil, why don't we start with you?
Yeah, this was great. This was very interesting for me personally, and I just wanted to say something to Max. Max, you said you didn't have any rocket engines on your balloons. I think NASA can help you with that. So, give me a call and we can hook you up.
Right on.
Perfect, thank you. Max, we'll go over to you next.
Yeah, this is fascinating to learn about what everybody's doing in this industry. We are extremely excited about the convergence of these technologies. We think terrestrial networks are here to stay, and they will continue to be deployed. We're excited that stratospheric networks are starting to arrive. Space systems have been here for a long time, and the kind of LEO systems that are being put in place now are amazing. Are things that nobody would have imagined even a few years ago. So I personally think the future is quite bright.
Thank you. Ed, over to you.
This has been great. Thank you, Diana, and other panelists. I think there's some good opportunities to extend this relationship beyond this session. And it's really good to hear the progress that you guys are making with the various systems. And look forward to networking in the future and appreciate the audience's participation as well. I think this is an exciting time for technology and innovation around wireless, and in particular, how we're going to build networks in the future.
Thank you, Jonathan. Final thoughts from you?
It just seems like there's a lot more excitement to come. So everyone stay tuned, and thank everyone for tuning in.
Great. Well, that's our panel for today. Thank you so much for joining us. Thank you for all the audience engagement and questions. And we're looking forward to continuing the discussions.
Thank you so much, Diana.
Thanks, everyone.
And thanks, Anna.
Thank you very much.
Yeah, thanks to all the panelists, and thank you to everyone for joining our panel discussion on the future of telecommunications. This conversation will continue in 30 minutes during the next session. The next session will be Filling Technology Deserts with Space, starting at 12:30 Eastern Time. Please join us again then. Thank you all.